as I said, what we are going to learn this time is probably new to everyone. Everyone, like except for a couple of people who already know the series expansion solution. So the problem is stated like this, like in this figure, we have a rectangular pipe, right? Rectangular pipe, and then left, right, bottom of the pipe are held at potential V equals 0, but the top portion of the pipe is V0, which is different from 0, right? In this case, the problem is what's the potential distribution inside the pipe, right, as a function of X and Y coordinates. And then in order to do that, our approach was first express V as a product of X and Y function, right? X only depends on X, Y only depends on Y. And then if you rearrange the term, you can make an X function dependent term and then Y function dependent term, which is equal to a constant number, right? The reason why this is constant number is because, you know, this can only depends on X and that can only depends on Y, so that there's no way that lambda can be dependent on X or Y, right? Because otherwise it's gonna, it does not agrees with the definition. So lambda can only be a constant. And then from that, we could obtain a solution for X function, which is a sine and cosine functions. And then we apply the boundary condition, X boundary condition, X equals 0, X equals B. And then from that, we know that X function must be a sine function, not a cosine function, right? So it should be sine function. And then, and also this lambda must satisfy this condition. Lambda should be n pi divided by b. And then n can be only integer, okay? And for each x, you can also obtain y function. And then if you apply the bottom boundary condition, you know that y should be sine hyperbolic function. And then because we have a degree of freedom of choosing lambda, right? Lambda, we have like many number of available possible lambdas, which can be defined by n pi divided by p. So we have like many of these. So sine hyperbolic n pi divided by p, a sine n pi over b x. This equation, I mean this expression, again, satisfies all three boundary conditions, right? And also, this satisfies Laplace equation. So linear combination of these, any linear combination can be a possible solution for this. But we have to satisfy one last boundary condition, which is the top boundary condition. So we want to make a linear combination of this and then determine Vn, which is the coefficient to satisfy the final boundary condition. So the final boundary condition is this. When y equals a, right? When y equals a, then this becomes like that, like n pi divided by b a, and then n pi over b x. And then if we set like Vn properly, then it must be equal to V0, regardless of x, right? That's the final boundary condition. The question is, how can we find Vn, right? So here I'll tell you how to solve this problem. I guess for most of you, this problem looks too difficult, right? Too complicated to approach, right? But here, mathematicians figured out a very interesting way of approaching this problem. So before we talk about that, let's talk about vector, going back to our vector space for a short time. So let's say you have a you have a vector A, and then this vector is a linear combination of Cn An. Okay, so An is just the basis vectors, as we know, and then An are like mutually independent, right? So if you take An dot Am, it must be 0 or 1, like depending on whether M is equal to N or M is different from N, right? This is what we know. Like this is just an orthogonal basis system. So in this system, if somebody asks you, what is Cn or Cm, how would you get Cm? Like how would you determine Cm from this given equation? Let's assume that you know everything. You know A, you know An, then all the An expressions. Then how do we determine Cm, for instance? Can anyone type in? Inner product, right? As you said, you can take the inner product. So you can just take the inner product of Am, right? And then this part you can easily calculate. You can just take an inner product. And then here, you know that by the orthogonal basis system, all the terms other than n equals m goes away, right? So that this becomes Cn. I'm sorry, Cm. So Cm is equal to Am dot A. So that's how you determine the coefficient from this relation, right? And then the completeness of the An guarantees that this expression can represent any vector in the vector space, right? That's kind of guaranteed if the An is forms a complete basis set. And similarly, we can do the same thing for functions. This is very interesting thing, and you should be kind of accustomed to this concept. Okay, now our question is like this. You have one function that we know, and then we have like multiple functions, basis functions, that forms a linear combination to satisfy certain equation. So if we can somehow define like inner product for functions, then all we need to do is just to take an inner product on both sides, and then we get Cn, right? For each coefficient. And then that is possible, actually. So people, there are many ways actually to define inner product in function system, but the most common way is just taking multiplication and then perform integration within the domain, the domain that problem is defined. So in our case, it should be 0 to b, right? So if you take the inner product, then if these functions forms orthogonal basis, then it must be 0 if m is different from n, and then it should be some constant if m is equal to n. Okay, so if the functions satisfy this type of a relation, then this is called the functions forms a orthonormal basis, similar to the vector space. One different thing here is that vector space typically have a finite dimension, like 3-dimensional vector space requires only three basis vectors in order to span everything. But here, functional space typically have infinite dimension. So Gn, like the basis functions also have are infinitely many. Okay, but still it forms a complete basis. Okay, And then fortunately, the reason actually why we expand everything into a trigonometric function is because trigonometric function forms orthogonal bases. So if you have sine like nx and sine mx, and then take the inner product by taking integration from minus pi to pi, you can see it's 0 if m is equal to different from n, and pi if m is equal to n. Okay. So now I guess things are clear, right? Now it's going back to your problem. So this is your problem. This function, which is this v0, we know the value, is expressed as a linear combination of sine functions, right? And then all these things are just coefficients like n pi, b, a, vn. Like we don't know vn, but this is what we know already. So how do we determine vn? We can take the inner product. How to take inner product? Multiply sine m pi over bx on both sides, and then take integration from 0 to b, right? And because these sine functions form a orthogonal basis, things are pretty simple. So let's look at the repeat what I just said. In order to obtain vn, vm, for instance, what we need to do is to multiply sine m pi over b x and then take integration. So this is basically inner product. And then do the same thing on the other side. Multiply this, take integration from 0 to b, right? And then left-hand side, this side becomes, due to the orthogonal property, only n equals m term survives and all the other terms goes away. So when n is equal to m, you get sine squared m pi b x, and then this is this. Okay, this is this is just 1/2 b divided by 2, and then this is the equation. And then similarly, for the right-hand side, you can easily perform the integration, right? And then this is like a cosine m pi over b. And then if you insert 0, it becomes 1. And then if you insert b, it becomes cosine m pi. Okay, and the cosine m pi, of course, is either +1 or -1, depending on whether m is an even number or odd number. So this entire thing is 0 if m is even, and this if m is odd number, right? So now you know both sides of the equation, right? So from equating this and that, you can determine Vm, right? And then Vm is written like this. And m is equal to 1, 3, 5, and so on. Okay, so now Vm is determined. So the only thing left is just writing everything in one single equation. That's like this. So Vxy is equal to linear combination of sine hyperbolic n pi over b y sine n pi over b x. And then here is the coefficient that we determined. And then n here runs from 1 to infinity, and then n only spans the odd number, right? So that's the solution. That's the series solution. So if you write this solution converges to this infinite series converges to the true solution of this. And then this is how it looks like. When V equals V naught, this is the equation. When V is 0, it becomes like this. And then all the other equipotential lines written like in this dashed lines. And then of course, electric field, which is the gradient of the potential, looks like this. Like this. Okay. And then of course you can, when you first get the equation, you should first check whether this equation is symmetric with respect to the x equals b over 2. And then you can easily check this is actually symmetric with respect to the x equals b over 2, because it's basically a sine function. So sine function looks like this. So with respect to this point, it's just symmetry. And also n equals only 1, 3, 5, and so on. So it's like actually either this or doing this and so on, right? And some of you may realize that you can actually know, so in the previous step, as a result of calculation, like previous step here, as a result of calculation, only, so the Vm have value, non-zero value, only when m is odd number. And then when m is even, it becomes 0. Okay. You can also, of course, get to this conclusion from the equations, but more intuitively, you can think about this. You can think about this symmetry. So let's think about the symmetry of the system. When m 0 to b, when m equals 1, then this sine function should look like this. When m equals 2, sine function should look like this, right? When m equals 3, sine function should look like this. So with respect to the center point, b divided by 2, when n is an odd number, sine function becomes symmetric. And then when n is even number, as you can see here in this example, it becomes an anti-symmetry, which doesn't make any sense, right? Here, you should have a mirror symmetry here. So all the terms should satisfy this mirror symmetry, so that n, n and even n is not allowed in that sense. So you can just apply this symmetry even before solving the problem. If you are confident about this, then that will greatly simplify your calculation. Okay, so any questions so far? So you are going to do exercise of this similar problem, like you have a boundary values, and then you apply this series solution in our midterm assignment. Okay, and then you will realize how to apply this. But the important thing is, again, understanding about this basis functions and orthogonality between the functions, because that's the key. That's the key how you determine the coefficients. So ask if you have any question. Okay, no question. So was this easy enough? Or like you kind of understand this, but you may need some time to actually work on this by yourself in order to absorb. How? So was this like easy, very straightforward? Raise your hand. How many of you feel that this is easy? Raise your hand, please. Okay. Okay, then how many of you feel that this is incomprehensible? It's too difficult so that I don't know what's going on. Please raise your hand. Okay, so everyone else is in the middle then. It's not too easy, not too difficult, but you just need some time to get accustomed to it. So yes, indeed, I expected a similar thing. So you may need some time in order to absorb this, but you get the key points, right? First, divide, and then you get the series form and determine the coefficient by applying the orthogonality between the functions. And the orthogonality between the functions are very powerful because even though you have an infinite sum of functions, by just taking multiplication and then take an integral, you only have one term, right? And all the other terms just goes away due to the orthogonality. So that's the kind of beauty of how to solve this problem. And then this is one example of like series solution in XY coordinate. Okay, XYZ coordinate, so Cartesian coordinate system. And in here, we use the basis functions of sines and cosines, which forms, again, the complete set. Okay. And if somebody asks you, okay, how general this method is this gonna work for all problem? Yes, it's gonna work for all problem, but depending on the geometry, it will become extremely difficult, right? Like let's say you have some random shape boundary. Then the equation you need to solve becomes extremely difficult, so that practically it's impossible to solve that way. But in principle, of course, you can express anything in series solution. Okay. And of course, in midterm assignment or any assignment, the boundaries will align with coordinate axis, or at least like the 45 degrees, so that you don't need to worry too much. Okay, then just for your information, this is optional, and this will not appear any exam or any assignment. Just for your information, you can expand the same approach to other coordinate systems. Okay, and then in this case, what you do is you divide the function as a product of rho function, phi function, and z function, like in case of cylindrical coordinate. And then you do the same thing. You separate the variable, okay? And then you when you separate the variable, you assign like each function functional forms, and then z function. If you actually solve it, z function is an exponential function as a lambda as its constant. And then phi function is e to the im phi. This is just sine cosine function. And then here, interesting thing is that because if you think about the phi coordinate, the value at phi equals 0 and the value at phi equals 2 pi must be the same, right? They are actually the same point. Phi equals 0 and phi equals 2 pi are actually the same point. If I draw it again, like if this is x, y, and z, because this is phi, phi equals 0 and phi equals 2 pi are the same point, right? So this function, if you look at this, when m is an integer, this property automatically satisfied. Okay, e to the I plus minus I m phi, and then phi equals 0 and phi equals 2 pi, multiplication of 2 pi, they're all 1. So it's like automatically satisfied, this property. So no problem. And then rho function has very complicated functional form, right? And then actually the solution of this is Bessel function, what is called Bessel function. Okay, so the Bessel function, like a sine and cosine, like sine and cosine, Bessel function, we call it as a Jm function and the y functions, and they have all their own functional forms. Okay, and these three forms like a cylindrical harmonics, what we call cylindrical harmonics. This forms the basis functions for cylindrical coordinates. And then every function can be expanded into a series solution of this guy. And then all you need to do is determine the linear, the coefficients by solving the problem. So if your problem has cylindrical symmetry, this is the way you go. Okay, this is how you, the way you go. But again, this is kind of beyond our scope. So I don't want to go into detail. I'll just tell you that this exists. And here the same thing. You have a spherical coordinate. And then spherical coordinate, of course, you separate the function for r function, theta function, phi function, and then you can see the phi function looks the same, right? Oh, okay, this is not g, must be phi. So this phi function looks like this. R function is r to the L or r to the minus L plus 1. And then theta function, in this case, looks complicated, right? And then this equation, the solution for this equation has name of associated Legendre polynomials. It's complicated name, but it's just, you can just consider this as a just cosine and sine function, right? Cosine and sine also looks complicated, like going up and down all the time, but we just call it cosine and sine. And similarly, associated Legendre polynomials has their own functional form. And then it looks like this. So in spherical coordinate system, you can expand the solution into these bases. And then you determine the coefficients. Okay, and that's how you solve like the problems having spherical symmetry. And some of you may ask the question like, then let's say some structure which has, not exactly cylinder, but not exactly cube, but not exactly like sphere. Then which basis is correct to apply? Well, I would say that there's nothing like wrong about choosing different bases. So it's like this. Let's say you have a vector A. Okay, this vector A can be represented by using XYZ coordinate or R theta phi coordinate. Whatever coordinate, right? There's nothing true or false about choosing the basis. There's only convenient basis exist. And similar thing applies here. Like even for the rectangular pipe problem, if you want, you can choose spherical basis system. Then the problem becomes extremely difficult. So it's probably a foolish thing to do, but anyway, there's no problem doing that in principle. Okay, there's only the convenience. There's no right or wrong in choosing basis. It's just a matter of preference. Okay, so any question so far? Okay, Song Min Chan asks, why does the separation of variable assumed successfully? Okay, this is a really confusing point, right? When I first learned about this, it was also confusing. I was also kind of confused about this. But the answer is that is due to the completeness. Because the way I solve, to give you the solution looks a little bit like I didn't give you the answer from the fundamentals, but just tell you beginning from the problem and then going to getting to the solutions. But if you actually learn about the fundamentals of this functional basis system, you will learn that this sine and cosine basis forms complete set, which means you can express any function using that basis functions. So the combination of this can basically explain anything, express anything. So that's why it works, and then that is already proven. Okay, so yeah, so that's the answer. Although I didn't give you the proof, but that's how it works. And by the way, by any function means, of course, the function that satisfies certain nice properties, right? Like it shouldn't, it should be like I don't know, some nice properties. It shouldn't be like it's completely random, but it should satisfy certain properties. Okay, so any other question? But this is really good question, and then you should ask this type of a question like all the time, right? It's very confusing when you first look at this. Wow, this is work. What a coincidence, right? It looks like a coincidence that this approach works, right? Maybe this is just a special case that it works, but in actual case, it's not. It actually works for general case, in all cases. So, and then that can be proven by the completeness of the basis functions. And I cannot give you a long answer, like a long proof, like how or why this is the case. But you can kind of think in this manner, like in a vector space, for instance. Let's say we have three-dimensional vector space, and then we have three independent basis functions and basis vectors like A1, A2, A3. Let's say they form a orthogonal basis system. Then we know that in any vector in three-dimensional vector space can be represented by using these three vectors, right? We know that because the vector space is three-dimensional and we have three independent bases, then that's it. Right, we have enough set of bases that express anything in the vector space. Similar thing applies here. Like if you have a function space, and then we have although it's infinitely many, but like complete basis set, it can express anything, any function in the basis in the functional space. Interesting, right? It's pretty interesting thing, I would say. And then just at least to me, so I learned this when I was an undergraduate student. I learned this twice. The first occasion was learning from 응미 or 응해. I forgot, like 응용 미분 방정식 or 응용 해석학. I'm not sure which one was that. But anyway, I learned about this in that course. And the second time I learned about this was in electromagnetism class. And to me, learning from electromagnetism by solving electromagnetism problem was way more tangible, like way more easier to understand compared to when I learned from just from mathematics, because I kind of have some sense how this can be applied to actual problem. But anyway, this is one thing that I wanted to cover in this lecture. And the second one, if I move to the second phase of the lecture, we're going to learn about method of images. And some of you already know about this method, but maybe I will explain some of the not trivial application of this method. So the problem is like this. You have charge here. You have a conducting plane here. And then find V and E everywhere. So that's the question. Find V and E everywhere. So here, what's the boundary condition? The boundary condition is this. V equals 0 when Z equals 0, right? That's how you, that's your boundary condition. And also V equals 0 in this case when Z goes to infinity. Like if you go far away, must be 0. That's the reference point of the potential. So how to solve this problem? The problem, the way you solve this problem is just like treating the problem as if you have a negative charge with the same amount at a mirror position. Okay. And then just assuming this, and then look at the problem again. Let's look at the problem again. First of all, first the potential. The potential due to this guy is what we know is just a Q 4 pi epsilon naught and x squared plus y squared z minus h squared, right? And then potential due to this guy is negative Q 4 pi epsilon naught x squared y squared z plus h squared, right? Therefore, when z is 0, then what? Then this term becomes equal, so v becomes 0 for the entire plane. So the first boundary condition satisfied. Second boundary condition is v goes to 0 when like all the other parameters goes to infinity, and that also satisfies, right? This is just a simple point charge. So if you go to infinity, that becomes 0. So what does it tell you? It tells you that at least on this half, the boundary condition and the Laplace equation are both satisfied. So that this is the only solution by uniqueness theorem. Okay, sounds like a cheating, but it's like a kind of proper way to solve this problem. So let's look at this again. Again, this is the boundary value condition that I said. When z equals 0, v must be 0. And then when r is much larger than h, v goes to 0. And then here is the thing, like as I said, you put a imaginary charge on the other side of the surface, then you can see v is 0 on the conducting plane. So that's kind of a good solution. Okay, so that v becomes like this, and then you can, of course, you can evaluate E by taking the gradient, negative gradient of V. This is how you solve problem. And then that's where V and Z is larger than 1. So the upper half plane. And the lower half plane, of course, is a conductor. So V is 0 everywhere. Okay. So like that solution is valid. Like the putting a imaginary charge on the other side is valid only in the upper part. But in the lower part, V is 0, because this is kind of known from our previous solutions. So the actual solution should look like this. So what else can we know from this equation? We also know these things. First, surface charge density on the conductor. Second, total surface charge by integrating this, and the force and the energy. So let's look at the equation, the situation again. You have a conductor, okay, and then you have charge Q here. Here's the H. Here it's negative Q you put, but this is imaginary charge. So your electric field should look like this. Right? But that is true only for this region. So in reality, of course, you don't have charge here, right? In reality, this is just a conductor. So charges are actually distributed like this on the surface. You learn that charges can only exist on the surface of a conductor, right? Then how do we know? How do we know the distribution of the charges? Well, it's easy from the boundary condition. Like we learned about like a boundary conditions, like at the conducting surface, which was rho F is equal to dN. Right? You remember this. When you have a conducting surface, the surface normal component of the D field should be equal to rho F, right? The free charge density. So if you apply that, because you know already the electric field distribution on the surface, from that you can get the rho F. Okay, so it's like this. Rho Fs as the surface charge density is just nothing but dN dz, which is this. Okay, the total surface charge, you can just integrate rho s over the entire plane, which gives you minus q. Okay, so the amount of the charge on the surface, if you add them up, it's negative q, which kind of makes sense. And the force is F equals Q dot E, and then since you know the charge distribution, and then and then the electric field due to the charge distribution, if you calculate it, it's actually this, which is same as the case where you have a negative charge at the image position. And energy also, like 1/2 QB squared, you can easily calculate. Okay, so is there any question so far? Like throughout the process? Okay, so I guess Hwang Jinung asks about the previous part. So he asks, how can we assume like Vxy is equal to as a component of Vx multiplied by Vy? Again, you should not be confused about the assumption here and the solution there. Okay, so if you look at the solution looks like this. Vxy is like x function multiplied by y function plus x function 2 multiplied by y function 2, x function 3 multiplied by y function 3, and so on, like infinite sum, right? That's our kind of final solution form. And of course, this entire thing is not separable, right? It's not like x function and y function separated. But like before we get in here, in order to get just one part of this, we assume that x and y are separable, right? And then obtain x function and y function separately, like by applying the boundary conditions. And then because these x and y basis functions are complete, if you ended up having a linear combination of this, you can express any function. And that's why this was possible. But you shouldn't be confused that our end solution is not separable, right? Our end solution is just a linear combination of xy functions, right? It's not about like, you cannot like kind of separate x function and y function from here. I hope this answers your question, though. So we first so the reason why we did v is x function and the y function, the product of x function and y function, is because we want to obtain the expressions for the basis functions, x basis function and y basis function from that separational variable. Yeah, if you are still having unclear things about this, I recommend you to try to solve more problems, exercise problems, and then if it's still unclear, you can probably ask to me in the office hours. Do you have any question about the image charge method? Okay, Park Seun asks, can we do the similar thing for like other problems that we can replace the boundary conditions and Laplace equations? Yes, you can apply this similar technique for other types of problems. Yes, exactly. Not all problems. Like for instance, this one, the series solution, you can use it for the problems where your boundaries are aligned with coordinate axis. Then it can be relatively easily solved. And then for this thing, the method of images, you need also a specific symmetry in order to apply. But yes, there are many other examples that you can apply these techniques, and that's why we learn these things. Anything else? Okay, Kim Yuil asks, why this is your boundary condition? Okay, so this is also a good question. Like what he asks is that, okay, I understand that this is our boundary condition, but then why this is even needed? That this is what he said. And then let's think about the boundary, like the concept of the boundary. Like in our previous problem, we have rectangular pipe. And then we need to solve the problem inside the pipe. In this case, we have a finite area and the boundary is trivial, like it's just a rectangular pipe. And then it's enclosed by, the solution area is enclosed by this. And here too, one complication of this type of a problem is that we have open boundary. So one of the boundary is here, the bottom boundary, but the other boundary is the free space, right? And in this case, there is a possibility that you do funny things at infinitely far away region. So in order to our problem basically includes the semi-infinite upper half space. So our boundary becomes bottom one and the upper one, and this tells you about the upper one, the upper boundary condition. Okay, so you need to satisfy all boundary conditions. This is a good question, though. Is there any other thing? Okay, then let's move on, I guess. But before I move on, I just want to ask you, how many of you saw this problem before? Raise your hand. How many of you saw this problem before? This image charge problem. Can you raise your hand? If you saw this problem before, raise your hand. 1, 2. Only 3. Okay, 4. 4. Only 4 of you. Oh, okay. I thought that this is very famous problem, so many of you already saw about this, but it's not the case. Okay, well, anyway, this is how you solve problem, and then from now on, I'll give you more examples how to solve electrostatic problems using image charge method. Okay, the key is, again, satisfying Laplace equation and the boundary condition at the same time. That's it. Okay, then that's the unique solution, at least in the upper half. So that's that. Here, this is another example. So in this case, you have two boundaries. One is this, the other is this. Okay, and both of these are grounded, V equals 0. So can you tell me where to put image charges? Well, if we apply the same thing from the previous example, we can put one image charge here, minus Q, right? And if once we do it, then the boundary condition for this surface is satisfied. And then what we need to do is, okay, then now this boundary is unhappy. So how about putting image charge here too? Then now this boundary is happy. So is that the end of the story, or do we need to do something more? Is this the configuration that we were looking for? The putting a negative charge Q here and the negative charge Q there in order to satisfy the bottom boundary and the left boundary? Can anyone answer this? Yeah, so it says, yeah, people says, we may need something plus Q here. Why? Why do we need it? I mean, we have a strong feeling that we need something here, right? In order to satisfy, complete square. Park Se-hoon said V is not 0 in the origin. Okay. Yeah, this is one way to look. Yeah, yes, this is also true. Yes, that's true. But more seriously, if we like look at from the very beginning, putting minus Q here, bottom boundary is happy, right? But as long as we put minus Q here, then, you know, if you look at the bottom boundary, this guy is no longer happy, right? Because due to this one, the existence of another image charge, the charge balance has been broken. So the bottom boundary is not happy anymore, right? So in order to make bottom boundary happy, you need plus charge Q here anyway. And that applies to this boundary too. You need to satisfy the charge balance by everything, all the charges. So this is how you solve this problem. So the charges inside this region behaves, the potential inside in this region behaves as if you have 3 image charges at these specific positions, right? And that's the end of story. Once you put like this image charges, that's it, right? And of course, the force that this guy feel can be obtained by calculating the force due to these charges too. And then, of course, you can expand this into more complicated cases. Like you have a theta, which is like 2 pi divided by m, right? And then let's say you have a q, then how many image charges you need? You need like multiple charges here and there. And then what? This guy is not happy, so you need another charge there. And then once you have this charge, this guy is not happy anymore, so you need another charge there. And then due to this one, this plane is not happy, so you have another charge there, and so on, right? So if theta is commensurate, like 2 pi and theta has a integer ratio, then this process can be stopped with finite number, right? Like in this case, we have solution by having 3 more charges. And then even though you have a smaller angle, if 2 pi and theta have integer ratio, then the process of putting image charges ends in finite number. But if it's incommensurate, then, you know, becomes forever, and then this problem is not possible to solve using boundary charge. Image charge method. Okay. So now this is kind of a final. Oh, this is also a nice question. Like Park Jun just asks, can image charges only be placed within conducting objects then? Yes. The reason is in this region. So you probably realize that we did not put any image charge in the domain that we need to solve. And the reason is, if we have image charge here within the domain that we solve, then at this point, Laplace equation break, because we have like charge here. Because we know that no charge exists except for the original charge. But like, you know, once we have a charge there, then Laplace equation no longer holds at the point. Becomes a singular point. Okay, so here is a famous exercise of image charge method. So I will introduce this problem and probably give you some hints, and then move on, probably finish today's lecture. So the image charge problem you want to solve now is this. You have a charge here, and you have a conductor here, which has a spherical form, and then which are grounded. So V is 0. So the boundary condition you need to satisfy is, of course, V is 0 for when R is A, right? Can you guess where do you need to put your image charge? So first, where? Second, charge amount. This is not a simple problem, right? It's not like as trivial as the one we deal with plane. So one thing that we are absolutely sure is that the system has symmetry with respect to this axis, right? So if we put a image charge somewhere, it should be on this axis, right? It doesn't make sense that we put something here, right? It's a very stupid thing to do, because if we rotate the system, then image charge will be rotated, which doesn't make any sense. So image charge must be on this line, right? And another thing that we know is that image charge should be within this conducting sphere. So where then? Where in this sphere? Let me ask you a quick question. Like, let's say this is the center. Image charge, of course, should have a negative polarity, right? It should be negative charge. We are not sure about the charge amount, so let's say it's Q prime, negative Q prime. Should it be here, the left side of the origin, or the right side of the origin? Can anyone answer? Where should it be placed? Right side? Okay, right side. Why? Many people get the correct answer. Like Kang Yung and Lee Chung Pil said, both of them said right. Why? Why right side? To make surface potential 0. Okay, so Lee Chung Pil said 구명 겨울의 상. It said it's an image of a spherical mirror. Yeah, but more fundamentally, what Kang Yung said is just kind of more fundamental. So the potential due to this guy is stronger here compared to there, because this point is further away compared to that point, right? So in order to compensate the potential due to this original charge, new charge must be placed right side of the origin, because only doing so, this guy is closer to this one and then further away from that one, right? So bigger potential is canceled by bigger potential, and smaller potential is canceled by smaller potential. That's how it works. That's why it has to be at this position. And from that, one thing become also obvious. The ratio between, let's say, the ratio between, say, L1 and L2. What would be the ratio between L1 and L2? You can express this using A and B. Can anyone answer? What's the ratio between L1 to L2? Using A and B. Right. So as Kang Yung said, the ratio must be the same. So the ratio from like the length ratio from this charge to this point and that point should be equal to the ratio from this charge to this point and that point. So from that relation, the position of this guy is determined, right? And then this one, that is determined, and also the charge amount is also determined because we know the actual length. So, you know, if you compare the actual length and then knowing that potential is inversely proportional to the length, then you know already the charge amount. And then, fortunately, once you place Q prime at this position, not only here and there, but everywhere on the surface becomes zero potential. That's kind of a fortunate thing. Okay, we just guess the position and the amount of image charge Q prime by taking into account just this point and that point. But once we do it, and everywhere on the surface becomes zero potential. Okay, so that's how it works. So H becomes A squared divided by B, and then Q prime is equal to minus A divided by B Q. So that's how you put an image charge for a spherical system. And once you do it, potential is zero on the surface. So by writing the potential due to image charge and original charge, you can express the potential outside everywhere. And of course, potential inside is zero. It's just the sphere, conducting sphere. Okay, so this is pretty much all I want to say today. And next time in our lecture on Thursday, I will briefly recap this problem and then introduce you a little more complicated problems. And that'll be it for this chapter.